Okay, so in this video for Math 1560 Calculus 1 at U of L for fall 2017, we are going to look at the first part of the fundamental theorem of calculus. I hope I've got this right. I guess I just didn't change the title. This is part 1. Okay. So here's what the fundamental theorem of calculus part 1 says. It says that if you've got a continuous function on a closed interval and you define a new function via integration, as we see here, then you get a continuous function, you get a differentiable function, and the derivative of this new function is the one that you started with. So this says that integration can be used to construct antiderivatives. I'm going to focus on this part of the theorem. Of course, if we can establish the derivative, that gives us the differentiability, which gives us continuity on the open interval. There's a little bit more work to check continuity on the endpoints. We're not going to worry about that. Let's just worry about understanding why this works out. Well, I mean, you can sort of see what goes on, but let's think about how would you calculate it. How would you calculate f prime? Well, when all else fails, right, we don't have any derivative formulas that we can apply here. Chain rules are going to help us. So what do? We got to fall back on the definition. What does the definition say? The definition says that f prime is the limit, h going to 0, f of x plus h minus f of x over h. So what is this thing that we're taking the limit of? F of x plus h minus f of x is, well, that's the integral from a to x plus h, f of t dt, minus the integral from a to x, f of t dt. Now, think back to those properties of integrals that we did a couple of videos ago. One of them says that, if there's a minus sign out front, you can get rid of that minus sign by flipping the limits. So we can do this. That minus becomes a plus if I change places, if a and x change places. Okay? But we also have another property that says that if the lower limit for one integral matches the upper limit for the next one and you're adding them together, you can combine them into a single integral with the upper limit from the first and the lower limit from the second, right? And now we're dividing by h, so we just multiply by 1 over h. So what we've got here is the limit h going to 0, 1 over h integral x to x plus h f of t times dt. Okay, now we've got to see if we can calculate that limit. Now before taking that limit, let's just think about, well, visually what's going on here. If we had a graph, right, here's x plus h, right? Here's our rectangle, right? So, if h is really small, then we could think about kind of using one rectangle to approximate this area. And what would be the area? The area would be approximately f of x, which is the height, times h, right? And so that area there, this f of x plus h, what is that approximating? That's approximating this, which is f of x plus h minus f of x. So that means that this difference quotient here, what is it approximately? It's approximately little f times h divided by h. It's approximately f of x. Right, so this makes sense that f prime should give you a little f. How do you really nail this down? Well, we know that little f is continuous, right? So if f is continuous, we can use the extreme value theorem on this interval from x to x plus h. We can find mh equal to f of some, let's say, c1, big M equal to f of some c2, right, where c1 and c2 are between x and x plus h, and little m is less than or equal to f of t less than or equal to big M for all t between x and x plus h. Okay, now by continuity, right, continuity says that as h goes to 0, well, what's going to happen? As h goes to 0, x plus h goes to x, right? So c1, c2, they're both going to x as h goes to 0. And so that means that little mh and big mh, well, they both have to go to f of x since f is continuous. And so what happens? Well, what happens is that, and let's put it up at the top. So the integral from x to x plus h of f of t dt is less than or equal to mh, the maximum times the width of the interval, which is h, and it's bounded below by little m times h. Well, now I divide everything by h. I want that 1 over h. So that h is gone, that h is gone, right? So how are we going to handle the limit? Well, the thing that we want, the limit we want, is stuck in between these two values, little m and big M, and we know that little m and big M, they both go to f of x as h goes to 0. So what theorem are we using? It's our old friend, the squeeze theorem. The squeeze theorem tells me that this limit as h goes to 0 has to equal f of x. We've left out some of the details, but this is the basic idea. So extreme value theorem comes into the picture, squeeze theorem comes into the picture, we get the first part of the fundamental theorem of calculus. Alright, so what can we do with the first part of the fundamental theorem of calculus? Well, it tells us that we can use integration to construct antiderivatives, and it also tells us how to take derivatives of functions that are defined via integration. Right? So for example, in the first one, if f of x is the integral from 1 to x of 1 over t dt, well, what's f prime? F prime of x is got to be, well, so my f of t here is 1 over t. And the fundamental theorem says that big F prime is little f. So what's little f? It's 1 over x. One thing you might note is that in fact this big F, it is the natural log. Notice that f of 1 is 0, just like you have for the natural log. And in some calculus textbooks, this is how the natural log is defined. In some textbooks, you don't encounter the natural log or the exponential function until after you've seen the fundamental theorem of calculus. And the fundamental theorem of calculus is used to define the natural log as an integral, and once you've defined the natural log as an integral, then you can define the exponential function as the inverse of the natural log, and then you go from there. And in fact, you can derive all of the properties of the natural log. All those log properties can be derived using properties of integrals and this definition. Okay, let's try one more. So now this time, it looks really complicated. Don't let the complication of the function inside the integral throw you off. What you've got is f of t is t squared e to the sine t cubed plus 1, and FTC says that if you want big F prime, you just take little f and you evaluate it at x, so all the t's become x's. E to the sine x x cubed plus 1. Okay, now for the next one we do have to be a little bit careful, okay, because here what we have is you have something that looks like this, the integral from 1 to u of t squared e to the t dt, where u equals x squared. So this time you actually have a chain rule going on. You have composition, right? This function here we could think of as some g of u. So f prime of x, right, is going to be g prime of u times u prime of x using the chain rule. So what's g prime of u? Well, g prime of u is going to be u squared e to the u. Because again, fundamental theorem says you just take the variable of integration, replace it with the variable that you see up here. That gives you your derivative. But u equals x squared. So what we get here, u is x squared. So this becomes x squared squared e to the x squared. And then we multiply by u prime. Derivative of x squared is 2x. Okay. One more and then we'll call it a day. This time, notice that this time both limits depend on x. How do we handle that? Well, first we have to manipulate using properties of integrals. So this is, now I'm just going to, there's nothing special about 0 here. I just want to pick some number. X to 0, 0 to sine x. Alright, I know that I'm allowed to split up an integral like this. And then this first integral, I also know that I'm allowed to flip the limits here. I can write this as minus the integral from 0 to x of t squared dt plus the integral from 0 to sine x of t squared dt. Okay, so what's f prime? Well, the first one is straightforward. For the first integral, you do have just plain old x up there, so all we do is take that x, t gets replaced by x, we make sure we don't forget that minus sign out front, and we get minus x squared. For the other one, well, we've got to use chain rule again. So the derivative is u squared, right? But we evaluate when u equals sine x. So we actually get, so the sine x goes in for t. So we get sine x squared. We get sine squared x. But then I've got to multiply by the derivative of the inside part, and the inside part is sine. What's the derivative of sine? It's cos. Right. That's about as tricky as we can get for these types of integrals that you might, or these types of derivatives that you evaluate using the first part of the fundamental theorem of calculus. If you can work your way through a problem like that, you can handle pretty much anything that I might be able to throw at you in this sort of setting. Okay, so we'll stop here. We'll do some more examples in class, and we're going to look at the second part of the fundamental theorem of calculus next.